Dear students, in this video we are going to learn about the eigenfunctions and eigenvalues of angular momentum. In the previous video we have seen the various commutation relation and we have seen that the various components of angular momentum do not commute with each other. That means they cannot be simultaneously specified. But the total angular momentum commutes with any component of angular momentum. Here we choose Lz component. So the total angular momentum commutes with Lz component of angular momentum. That means both can be specified simultaneously and both of them will have the same eigenfunction. Now let us see what will be the eigenfunction for these angular momentum terms. For that we will revert back to the solution of rigid rotor, which is also a function of theta and phi and is given by the product of theta and phi function, which is together known as spherical harmonics and is represented by y Lm theta phi, where theta and phi are the variables and L and m are the quantum numbers. The Hamiltonian of rigid rotor is given by h is equal to L square operator divided by 2i. It means that the Hamiltonian is related to L square and the eigenvalue for the rigid rotor is given by E is equal to L plus 1 h square upon 8 pi square I. Here h is the Planck constant and I is moment of inertia and this L is the quantum number. Now from this eigenvalue of total energy we can easily get the eigenvalue for total angular momentum. Just let us look at the relation how they are related. L square is equal to Hamiltonian operator into 2i. So just multiply this by 2i, then what we will get? This we get. Okay. So whatever we get, that will be the value, eigenvalue of total angular momentum L square. This can be written as L plus 1 h square upon 4 pi square, and we know the h upon 2 pi is represented by h cross. So we can write this L square eigenfunction as L plus 1 h cross square. Now let us look at the operator expression of total angular momentum and that of Hamiltonian of rigid rotor. We see that both of them depend upon theta and phi. Here also it depends upon theta and phi. They are more or less of the same form. So the wave function can be represented by the product of theta and phi together, which is known as spherical harmonics. Thus we see that the eigenfunction of total angular momentum operator L square should be same as that of rigid rotor. And eigenvalue equation, we know that how we write the eigenvalue equation, the operator function, same function multiplied by a constant. So here the operator is nothing but this is L square operator, and what is the function here? This is the spherical harmonics. This is equal to, here we will have the same YL m theta phi spherical harmonics, and this gives the eigenvalue, and we have seen that the eigenvalue for L square is nothing but L plus 1 h cross square. So this is the eigenvalue equation for total angular momentum L square spherical harmonics is equal to L plus 1 h square upon 4 pi square. This it can also be written as L plus 1, this is h cross square, and this is the spherical harmonics. And if we take the atomic unit h by 2 pi, that is h cross can be taken as 1 unit. And in that case, we can write this as L plus 1 and the harmonics, spherical harmonics. So this is the total angular momentum, the eigenfunction and the eigenvalue. Now coming to the Lz component, we have seen that the total angular momentum commutes with Lz component. That means the eigenfunction of Lz should be same as that of L square. So again we see that this is nothing but this is the spherical harmonics. And spherical harmonics, it is the product of theta and phi function. And we have already seen this theta and phi function. Theta function is nothing but the associated Legendre polynomial, and phi function is given by this expression. So product of these two will give the eigenfunction for both L square and Lz, and it is same as that of for the rigid rotor. Now let us see the eigenvalues of Lz. Again going back to the eigenvalue equation, A psi is equal to constant psi. Here we will take the operator Lz. Lz psi is equal to constant lambda psi. The Lz operator is given by h upon 2 pi iota del upon del phi. So substituting this value here, we get h upon 2 pi iota del psi upon del phi is equal to lambda psi. If we rearrange this, we get del psi upon del phi is equal to 2 pi iota h lambda psi. Just separate the variables, bring this psi and phi on the other side and integrate this. We will get the solution of psi is equal to exponential 2 pi iota h lambda phi. We know that this exponential of this form can also be written as cos x plus I sin x. So you can write either way, either in this form or in this form. Now the psi should be single valued, finite and continuous. We have seen this condition. So if psi is to be single valued, this phi, we know that it ranges from 0 to 2 pi. Any value of phi should repeat after 2 pi. So whatever will be the solution of phi and whatever will be the solution of phi plus 2 pi, they should be same. So here we see that exponential 2 pi iota h lambda phi, this should be equal to that of phi plus 2 pi. On simplifying this, for 2 pi h lambda, let us write a constant. You can put any symbol k or m. I am taking here m. So exponential I m phi is equal to exponential I m phi plus 2 pi. That means this is nothing but this is exponential I m phi product exponential I 2 pi m. If we compare these two, we see that this term should be equal to 1. Okay, for this condition to follow, this should be equal to 1. So here we see that exponential 2 pi m is equal to 1, or it can be written as in trigonometric form cos 2 pi m plus I sin 2 pi m. This should be equal to 1. And this condition is only possible if m is equal to 0, plus minus 1, plus minus 2 till plus minus n. We know that m is given by 2 pi h lambda. So rearranging this, we can get the value of this constant lambda is equal to m h upon 2 pi. That means lambda, the eigenvalue of Lz, must be either 0 or integral multiple of h upon 2 pi. Thus, the eigenvalue equation for Lz can be written as this is the operator, this is the eigenfunction for Lz, that is spherical harmonics. This is equal to m h upon 2 pi spherical harmonics. Or this can be also written as m h cross y, that is a spherical harmonics. And if we take in atomic unit, we can write h cross as 1, and this can be represented like this. Thank you.